All right. Today is going to be, we'll cover the IonQ strategy for QHPC integration. So I'll hand it off to the IonQ team and they can take it from there.
Awesome. Thank you, Amir. Can everybody see my screen?
Yep, you're good.
Awesome. Cool. First thing we'll do is, as soon as I get clicking, there we go. Start out with a quick round of intros, and I'll let our team round robin. I think most of the folks on the call have seen me around on here. I'm the TPM responsible for hybrid integration at IonQ. So pretty much any project that is the classical world touching the quantum, I'm the program manager trying to keep track of all that and keep it moving along. Yuri?
Hi, my name is Yuri Shinder. I am the software architect for the Quantum OS, so the software that runs our quantum computers. And my background is in computer systems, distributed systems, performance analysis.
Cool.
Spencer?
Yeah, hi, I'm Spencer. I'm working on our SDK integrations, and most recently I've been doing some of the QRMI and QDMI plugins, as well as the project with NVIDIA and Amazon, the big hybrid thing that we did. So I've been very involved in hybrid, and I'm excited to help with this presentation.
And Gwen?
Hi, everybody. My name is Gwen Prawira at Mojo. I'm just joined IonQ a couple months ago. I'm the engineering manager of the developer tools team that Spencer is also on, and formerly quantum engineer, quantum software engineer, and quantum error correction at Microsoft and Rigetti. Mostly background in experimental physics, so transmon qubits, but now moved more over to the software side. And I won't be presenting any slides, but I'm definitely here if anybody has questions. Thanks, Josh.
Yeah, thanks, crew. First thing I wanted to do is, I figure most of you have probably heard of IonQ. I wanted to just give like a super high level overview of IonQ company and just kind of explain where we fit specifically. We've gone through several acquisitions, as some of you may have heard of the news. And the big thing that our company is working towards is being a full stack quantum provider. So when I say full stack, I'm referring to that the goal is to provide, a system. If it involves quantum in general, we're trying to offer it. So be that a security product, be that a sensing product, be that a networking product to try to bring it together. And last but not least, computing, which is where we all sit. I brought this diagram to kind of show you that we are the merger of basically Oxford Ionics, and we are kind of in a slow shift of shifting our architecture from what I'll just call legacy IonQ to the new Oxford Ionics technology. And today what we'll be focusing on is we're trying to give a high level picture of all of that. And there may be a couple areas that will change, but for the most part, that's mostly down in the lower control system is where the Oxford tech will come into play. But specifically, Spencer, Yuri, Gwen, and I, we all sit in the compute division, and the idea is we're going to kind of be a nexus of all of these variety of technologies coming together that, ultimately I wouldn't be surprised if some of the tech some of you are working on would, be in similar type nexus. And one other thing I was going to say is please interrupt as we go along in this presentation. Feel free to ask us questions. Kind of how we're going to go along here is we're going to start at the top on the cloud and then dive down until we hit, about the control system layer. And with that, I actually will hand it over to Spencer to start talking about our front-end APIs.
Cool. Yeah, thank you, Josh. So I'm Spencer, as I mentioned. I'm a staff engineer at IonQ. I work on our dev tools teams, our architecture, or our SDKs. And I want to talk about, from the perspective of a user, diving into our quantum platform. And I kind of wanted to focus on QDMI because I think it's relevant here. So as we can see from this layer, most people come in through like Qiskit, or they come in through a cloud provider like Bracket. All of those are making REST API requests to the platform. Can I go to the next slide? So here's an example of QDMI. We recently did an integration with them. So I wanted to kind of look at the methods that QDMI exposes, how those talk to our API, and then dive into our API. Where you see the QDMI rectangle, that tall rectangle, that's kind of like where a third-party integration would sit. It sits right between the QDMI and the devices, and all we have to do is make sure that those methods that QDMI is expecting are, mapped correctly, and so on with the with what our API supports. Can I go to the next slide? Yeah, so here's a bit more specific. I wanted to show, I guess, two interesting things. One is the mapping makes a lot of sense. If you want to create a job, you just fill up that method and make a put request to the jobs endpoint. But the interesting thing, I think, was QDMI is almost expecting more of a synchronous system. And when you have it talk to an API layer, that's like an inherently asynchronous system. So there's a little bit of a mismatch there. And I think it's interesting because it allows you to put QDMI at any level of the stack. And I really like that feature. So right now we're at the stack of the API level. And we made it work with async, which is fine. These are just some different methods. I don't really have to get into that. Next slide. But generally speaking, no matter what SDK you're using or how you're coming into the platform, you're going to follow this kind of life cycle, maybe this kind of path. You'll have an SDK client that makes a request to our API layer. Before you actually hit our API layer, we'll authenticate you. We'll make sure that you're not spamming us with too many requests, and we'll start like OpenTelemetry logging on it. And then from there on, we'll map the API key or whatever to your user, so we can add that to your job dashboard, and we'll start tracking the event of your job. And then we'll process the job. We'll make sure it's a valid circuit. You're not using too many qubits or whatever, or too many gates. Then we'll compile it to our native gate set. Everything that we run is in our native gate set always. And then we'll apply error mitigation. So we might create, a bunch of more circuits to run. And then when those all do run on the simulator or the QPU, we'll aggregate the information, the results, and we'll send you back a single URL that you can query. And I want to talk a little bit now about the architecture. I kind of, sped past it a little bit. If I could go to the next slide, Josh. Thanks. So as I mentioned, I talked about how like the SDK like QDMI will make a REST like an API request to our API gateway, and then that will, if everything goes well, you'll be in our services. And what happens then is a job comes in and is handled by the job manager. The job manager is going to create an event on the message bus. So here it's pub/sub, and when that event is made, it'll be like, hey, we need to compile this job. So it'll send out a compile event, and then the compiler will pick it up, handle that compilation, and then send the next message down into the bus. So the job has this life cycle where it is passed from service to service, and its state is updated as it runs. So what's really helpful there is we can actually I'll get into why that's so great later. But we also have like our telemetry and our alerts that all communicate through the message bus as well. So it's this central hub of communication that makes it really easy to add new services, to debug, etc. So that's kind of how our architecture looks zoomed out. And then next slide. So this is really great because, as I mentioned before with the message bus, it's really easy to add new services. All that is required is you have some way to add a new message to the message bus that another service knows how to pick up when it's detected. Maybe something that is less like more of a surprise, but in a really good way, was the OpenTelemetry. When we added that later, the different context and the like tracing ID that you would use for any event, it moves very easily along the message bus as well, regardless of what language we're using. If we're using Go and then we use Python for the compiler or whatever, all of that is traced very nicely through pub/sub. The other great thing is if you're having large scale simulations or you're doing intense compilation, sometimes a service will crash. And what's very helpful is if your event, for example, if there's not a simulator that can support the size of the job that you've submitted, you don't want that job to be sitting in the like queue stage forever. So it's really convenient to have monitoring and error reporting set up so that if a job is in a state, like a non-final state, right, for too long, we can automatically scale up the simulator. We can scale more, we can create more simulators. We can do all of that. But, you know, with all these benefits, there are some drawbacks. One of that is there's no shared schema language. So we have different implementations of those messages that PubSub that we're expecting to parse from PubSub and read from PubSub. So that would be something that you want to follow. Do not repeat yourself. So this is not totally great, but it's fine. I think the bigger issue is the path that the job takes. Actually, I put that in weakness and surprise. The path that the state takes actually bounces around quite a lot because we have a lot of different services. The benefit of that is we were able to add like a hybrid service that we used for the NVIDIA project. And in a case like that, we're running a bunch of circuits and we're doing heavy post-processing. So the jumps between the different services wasn't a big deal. But if you have a lot of small jobs that you're running back to back, it can add up. So there's a latency on the PubSub, and it's kind of a give and take where up until recently, it's been great to be able to add a service because that's like we've been growing and adding new features, and that's been like the highest priority for us. But as we get into more of this hybrid ecosystem and this hybrid landscape, we realize that it's becoming more and more important to drive down latency as much as possible. So for the solutions, and Erie's going to talk to this after me, one of the big solutions we have here is to use something like gRPC, where you get a lot of the benefits of PubSub without some of the latency that you'll accrue as well. Also, some of our core components, we are using JavaScript in some places, TypeScript in others, Go and Python, and some of those languages are great for typing, and they give you, a lot of security in that way. Others just are not good at all. So, like, I guess if you're designing a backend, you really want to make sure that if you're using Python, you're using something like MyPy or the new one, Ty or something. There are really great options that are built in Rust, so they're super fast. But yeah, you want to have typing. That's like super important. So I'm excited to pass it off to Erie. He's going to talk about the software stack, or one level below me. Yeah.
Thank you, Spencer. So kind of continuing on that path and kind of want to highlight the architecture of our software stack. And so as you notice in this picture, I'm kind of peeling the onion down a little bit and looking at 3 different distinct layers or subsystems, right? So Spencer talked quite a bit about the quantum platform. So that's on the way, and that's at the highest level. And that kind of operates either in the cloud or controls many QPUs, or can be co-located on premises with the QPU itself. So the middle layer, and I'll be focusing on that, what we call Quantum OS, and that's really the software that operates or runs the quantum computer. And so there are several functions that I will talk in a bit. And then at the lowest level, we have the QPU hardware with embedded software and programmable logic that executes programs at the lowest level. So looking at this kind of as a flow through the layers and the components and functions, we have users, they submit programs. We have a high-level schedule that figures out how and when and if to schedule a job. We go through the compilation layers, create optimized circuit expressed in our native gates, and then depending on the target architecture that the compiler decides, we can give it to a queue for the simulator or enqueue it for the queue for the QPU itself. And then we have the next layer down, the Quantum OS, and basically it has similar components. It has its own scheduler, so that scheduler decides when and how to pull when the system is ready and calibrated and online, the jobs from the user QPU job queue and interleave that with calibrations, right? So as we all know, we need to run every once in a while calibrations to figure out everything is correct and generate sort of calibration parameters that we use for sort of the lowest level of compilation and creating the microcode based on the actual state of the system, right? So we take the sort of a optimized circuit in native gates, we annotate it, we substitute sort of the latest values that we have from the calibration runs, then we generate instructions for the programmable logic, and we execute them on the QPU. And then obviously collect results and give them back to post-processing, back to the quantum platform. So as you notice, there's kind of a flow of different structures of, through different components that are self-similar. And a lot of the lessons and things that Spencer talked about applies in here. The components are written in different languages. We are moving towards sort of a concurrent strongly typed languages, and as needed, we go down. So let's move on to the next slide, where I talk a little bit more about sort of the multi-level scheduling decisions we make. And so as you noticed on the previous slide, we have basically several places in the orange boxes of where decisions are made. So at the highest level, the quantum platform, we make long-term decisions, basically figuring out how do we satisfy the service level agreements with different customers, and how do we do a fair allocation of the QPU resources for customer and for priority of the job, and also allow sort of for exclusive access for certain applications that have iterations. Then at the sort of a fine-grain per QPU job scheduler, or the automation scheduler as it's called on the previous slide, it's at the quantum OS level. And that decides, is the system ready to operate on user jobs? How to interleave calibrations with user jobs? And basically for efficiency, which I will talk about a little bit later, we dequeue multiple jobs from the per QPU jobs that were submitted through the platform and ready for execution. And then at the lowest level, we have a real-time scheduler that operates at the nanosecond precision to do all those sort of a low-level control. But it's the quantum OS that determines sort of the sequence, or the ordering of which calibration and or user jobs we schedule for execution next. So as we all know, the QPU is sort of the single execution context that we all care about, and so that's sort of in the nature single-threaded in that regard. So let's move on to the next slide.
Can I ask one question really quick?
Oh, absolutely, please.
For the quantum, as you say, interleaves user jobs. So does it mean you're interleaving only jobs from one user, or is there actually different users you can interleave at this point already?
It's really different users, right? The platform makes the high-level core decisions. How proportionally share between users, tenants, organizations, what have you, and really sort of what the quantum OS or the QPU sees is a queue of ordered jobs of different sizes, different circuits complexity, etc. But really, from the point of view of quantum OS, at the what I call the automation scheduler, or this fine-grained per QPU job scheduler, a job is a job is a job. Some of them are calibrations, some of them are user jobs, and they are from different users, right? And so, indeed, that's a good point. There's sort of a handshake, it's a cooperative scheduling. We can go more into detail maybe in the discussion, but really get kind of that's the strength, and kind of the decoupling is important, right? In that regard. So any more questions?
No, that helps. Thank you.
Yeah. And yeah, this is a very good topic. We can dive into this. All right.
So just another question. So sorry.
Yeah, please.
Yes, yes. Exclusive access are controlled by the quantum platform. This is very front end. Then maybe in that case, user jobs will be interleaved from the calibration job. Is that correct? In that case, or for example, a user want to do the, or some developing some noise model inside hardware. So, but calibration will be happen. In that case, noise model will be changed. In that case, the user want to get some calibration information from the hardware, and then need to create a noise model. So in that case, user can user get information about calibration event from the hardware side?
Yeah, so Josh, if you don't mind flipping to the previous slide with the picture, maybe easier to describe that, right? So you're correct, right? But the way and kind of what I want to convey here that we have scheduling decisions of different grain at the different layers, right? And so kind of how we think about it today is that the system itself, the QPU knows when it needs to be calibrated, when the fidelity isn't right, and obviously it monitors, the outcomes of each job that it ran. And so what we think of it is kind of encapsulating calibration from the high-level user. Obviously, they are like internal users or other kind of things where people may want to schedule calibration. So we have the ability to kind of come into the calibration job queue for sort of a just-in-time, if you will, calibration or manual calibration. But really, kind of the way to think about it is that the the decisions are cooperatively made. They're in different level, but really kind of a calibration is, if you think of it as sort of an internal to the system, different calibration, different length, different intensity run. So, we can, and we will be discussing more what and how much to expose about the calibration to kind of the end user that really thinks about using sort of applications, in a different model, kind of in a tight loop with lots of small circuits, but many iterations, or kind of large circuits, lots of shots kind of that run for a long time. So indeed, that's kind of is the crux of that. But for that, we decided to think about them separately, right? That the platform at the highest level, we intentionally don't kind of muddy or provide way too much detail about the state of each QPU to make the decisions that are sort of a high level or business oriented. Hopefully this explains something. And again, we can discuss more. Because I think that's the open question. How much to hide, how much to expose, and really what kind of a user or or application should know about calibration at all, right? And so that's kind of how we think about it, and that's how we decided kind of to separate this into separate layers and encapsulate it into each kind of a subsystem, if you will, right? The quantum platform, the quantum OS, and calibration, doesn't really matter at the QPU hardware execution.
Thank you so much.
Okay. Great.
Yeah, and Hiroshi,
right.
The only thing, Yuri, if I may add, is that there's another view of this diagram that I think specifically I would want to raise one point of, I don't believe, and Spencer and Yuri, jump in if I'm incorrect on this, I don't believe we passed the raw results of the calibration data back up for end users. We do have that for internal debugging.
Yes.
We have another view of this diagram that there's kind of an injection point right here for internal usage. So we do have that information, Hiroshi, more for our internal debug, but that's not something we typically pass all the way back up for an end user.
We give aggregated calibration data and characterization data. As for like more fine-tuned, we like that stays more on the internal side. Yeah.
Indeed, right? There's only so much detail you can fit into this. So you can, if you correctly trace the path, so if calibration routine is running and it's, just finished execution, we collect the results, but we give them back to the calibration routine's logic, if you will, and then updating the state, and that's the internal path, right? As opposed to finishing a user job where the results come out and are post-processed at the quantum platform, right? So all the good points. Yeah. All right, so on the next slide, Josh, please, number 16. Right. So if you are paying attention, there's lots of queues and lots of possibility for latency and delay, right? So how do we actually effectively improve throughput of the QPU, right? So that's the most expensive part of the system. So we do a sort of a tested technique, from computer architecture called the pipelining, right? And so you notice that, as part of executing a job on the QPU, on the quantum OS software, there's multiple layers. So we have sort of 6 stages of the pipeline: fetching a job, or multiple, from the queue, binding parameters, generating instructions, loading the microcode into the programmable logic, executing it, and finally uploading the results. So that's kind of an illustrative 6-stage pipeline. And what I want to illustrate here is that at time 1, each different job, so think of it, job 1, 2, 3, K, whether it's a calibration or whether it's a user job, again, is not important from the point of this picture, but we execute different job at different stage at points. So at time 1, a job 1 is executing on the QPU itself, and we are loading into the QPU hardware the next job, and then we are generating instructions for the job after that, the job 3, right? So then the kind of clock advances, and this is all just a illustration, where the pipelines are equally sized and the jobs are equally sized. In reality, that's not the case, right? But at T2, some logical time next after T1, we basically finish executing job 1, so we are uploading it back to the platform, and for the user to consume, we are executing job 2 that was previously loaded, and so on and so forth, right? So this is kind of a classical pipeline, and in T3 we shift again, etc. So notice that T1, T2, and T3 are not equal intervals, right? It's solely governed by the most precious, or the governing part, which is the execution, but it kind of helps us think about that. So what this does in this pipeline, we have we have put in the pipe multiple jobs from either calibrations or from the user queue, from the platform, and then we are kind of working on them at the same time in the software. So we have concurrency. In reality, though, we kind of run one job at a time, and at each stage. So Next slide, unless there's a question about the pipelining. All right. I think it's pretty straightforward, right? Computer architects understand this. They have been doing it for a long time. We do it at a high level with software components. And so why is pipelining important? Because this is a way to achieve concurrency, right? Even though in reality, we are executing one job at a time on the QPU hardware itself. And sort of, the graph on the right is just the illustration to kind of show the normal, utilization versus sort of, on the x-axis, the pipeline depth, or how many jobs are we kind of working concurrently on, if you will, at different stages. And so on the x-axis, as we increase the pipeline depth, so let's say 6 in our picture, or we improve the multi-programming level, which means how many user jobs we are kind of admitting to the Quantum OS or the QPU. The higher the number, intuitively, the larger utilization of the QPU. And that's really what it's about, right? But obviously, it's not as simple as this picture. We have jobs of different sizes, so for small jobs, few gates, fewer shots, the amortization of that sort of overhead is lower, and therefore it takes a while to basically fill the pipeline and sort of reach the utilization that we would like, versus for something that's a typical or large job as well, right? So the takeaway messages from this sort of a pipeline execution model is that we process things in stages. We have multiple things that we pull from the queue, whether it's the collaboration queue or the user jobs, and we kind of process them at the same time. And then we do things one at a time on the hardware itself. All right, any questions? So I think we can go to the next slide, right? So kind of to summarize kind of what are the mechanisms for efficient job execution, right? So at the highest level, we use, again, tried and tested technique from computer systems, proportional and partial scheduler, to make sure that we meet all the, no customer job is starved, no customer is starved, and then we meet all the SLAs. So based on the, how many shares we have and how we apportion each QPU, we make sure that everything is fair by some definition of fairness. But that's not sufficient, right? We need, in order to actually be effective at scheduling, we need a sort of performance model and estimators for how long will each job take once we actually know what is the optimized circuit in native gates. And we also have sort of a capacity of the QPU, because it's not that the system is available 100% of the time, right? There are calibrations. There's things that we need to do. Sometimes you take the system for maintenance, right? So collectively, the capacity, what fraction of time is the system available for executing jobs and not calibrating, and how available it is, and the performance of the thing kind of give you an estimation, or can feed to our models that we use at the highest level platform schedule, if you will. And in order to make that all possible, we have a lot of telemetry. Spencer already alluded to it. We have lots of instrumentation. We feed real-time data. And so we actually estimate what the job execution time would be on the QPU. We actually measure it, then we give the data back, and then we can sort of update our models and make better decisions as we go along, and update obviously our sort of a proportional share and allocation of shares to each tenant or to each job.
Hi,
Right.
May I ask a question?
Yeah, question? I guess.
Hi, this is Andres Paz. Quick question about your estimates. And I'm not sure, maybe, do you guys support classical control flow on interleaf on the execution? And if you do, how do you perform those estimations of costs? And I guess because if you don't, I guess it's pretty easy, it's just a list of instructions.
So I can give you a brief overview, and we can talk more maybe at the Q&A. So basically, what we mean by estimating, so each architecture, right? Each species and each architecture, generation of architecture of quantum computer basically has certain parameters. So we have a large group of the system architecture performance group that sort of figure out how a circuit of a given size, number of 2-qubit gates, number of 1-qubit gates, and parameters of the architecture and the species kind of figure into executing that job. So that's kind of a performance model. Then we kind of estimate, we know how long it takes roughly to compile or push it through the stages of the pipeline, but that's what we use. So I think that kind of, we don't have a, that's a kind of a description of a classical control, if you will, right? So we account for these parts in our performance model, and then we really use this at a high level to basically figure out when we schedule this job, we estimate it's going to use this much time and wall clock time effectively, right? And is the SLA or is the contract still allowing for the customer to run this? That's kind of an example of a decision that we can make. The other one is, again, if you have a small circuit with few gates and few shots, we know based on sort of a analytical model that we have built throughout sort of the stages, kind of when we first designed the architecture and the next generation of the quantum computer, when we sort of put it together and measure it, we can estimate how long that job of the same, of the same user program written in Qiskit, how long would it run on our Forte enterprise architecture or on our sort of ARIA architecture, right? They will take different time because the native gates are different and timings are different and the species are different and all that stuff kind of figures in there. So that's kind of what we have in the model.
Sorry, I didn't mean to disrupt. So go ahead.
Oh, no. This is great. This is meant to be interactive, and this is all evolving, and we are all learning and sort of discussing that here. So
perfect.
All right.
Sorry. Thank you.
Good. All right. So basically, as I said, we need all these three things, mechanisms to basically be able to do effective scheduling is the high level message from here. So maybe we can move on to the next section, and then look at sort of the things that we have learned along the way, right? So first thing that I want to kind of say, and that's kind of by itself, but has been proven very effective, is the power of Kubernetes. So some of you may know it's sort of an orchestration platform that we use very heavily for the quantum platform from the Quantum OS itself. And it really has been very useful in putting together a reproducible system. So obviously it has benefits for production deployments. We can do control upgrades. We can upgrade services. Spencer talked about, we can do control rollbacks. We know what kind of versions and softwares and libraries are on a given sort of a production, pre-production or development system. But I think what's more important for sort of this forum is that it gives us reproducible dev and test environments, so we can say, hey, make it look like how the system would look like, or how we think it looks like, or how it looked like when we had a problem. And so that's kind of the one use case for the dev and test. And the second one, I think even more powerful, is that we can actually put together the entire software on the system. We can build an emulator of the entire quantum computer, including the platform and the Quantum OS, and measure in situ what it would take. But obviously we don't, if we can remove the hardware, we can figure out the estimated model for sort of performing on what we call on ions. And then we have a reproducible full emulation environment, which is super useful for sort of this effort where running things on a quantum computer is expensive, but we can actually test everything, including the effect of queuing, the effect of message bus that Spencer talked about, and the effect of how many stages we need, and figuring out performance issues. If our compiler is too slow, or we have some issues, then handling states. That's sort of super useful. So Kubernetes has proven very important for putting together all the software layers, not having to rely on a real quantum computer because the hardware is expensive, and being able to sort of reason about and improve our scheduler, improve our mechanisms, and give environment for development of QDMI, QRMI integrations, etc. All right, so next kind of thoughts, and I think this was, is another kind of thing that has been very important and useful to us, is the using interface definition languages. So, Spencer mentioned that we sort of have heavily using protocol buffers. So that's a sort of something that allows us to define strongly typed messages in a IDL, interface definition language. And then we have automation or CI/CD pipelines that generate bindings automatically for each target languages. And as Spencer alluded, we have lots of different languages components, some of them in sort of a weakly typed scripting languages, some of them in strongly typed concurrent languages. So that's very important. And then, on top of it, when we have a sort of a strongly typed messages that are verifiable, we have gRPC as a mechanism for communicating between a client server. And again, we have automation and pipelines and CI/CD that allow us to generate client code base automatically, server side, and basically not worried about it, how we define a contract. And then everything is sort of push a button and we generate those bindings for the target languages. So that worked quite well for us, and we continue leveraging it and turning more internal kind of initially developed proprietary interfaces, whether it was originally JSON, into something that's sort of a more sort of a software engineering and sort of a best practice driven. Right. And so
And I saw one hand if you wanted to ask a question.
Sorry, I don't see that very well, but please, yeah, thank you. Yeah. Yep.
Hey, thanks, Yuri, for the very nice introduction, especially some final thoughts. So in your Kubernetes slide, you mentioned something around the QPU simulator for especially for full system emulation. I'm actually working on something along similar line, but of course what I'm working on is rather low level, so which is really down to the post level kind of simulation. So could you share a bit more about what kind of simulation are you looking at for this QPU simulator? Yeah.
Right. So we have people who are much more versed in this than I am, but imagine, basically writing a simulation model in Python, right? So my colleagues who are much more versed in sort of the low-level simulation and the noisy simulator that Spencer mentioned, right? So that's something written in, let's say, scripting language Python, because it's developed and the speed isn't important, right? So once we have that as a core, we can wrap it around in with the sort of a service contract, with the protocol buffers as input output messages, and the gRPC as sort of a client server remote procedure call. And then and that's actually what we do is we pretend that we run a circuit, we simulate it, how it would run. Obviously, depending on the complexity of simulation, it may take a lot longer time than running on a QPU, almost always does, but that's kind of is what we do. But what's important from my perspective, the simulation is then encapsulated as if it were a real service. And so we actually use it heavily. We do nightly sort of integration tests, and we don't use the low level detailed noisy simulator that we offer to the platform, but we have a very simple simulator that says, yep, I executed your microcode, the hardware said this is the result, and that's kind of what we built into our environment, and that's the emulation, right? So each service, so think of the QPU hardware, which sort of I glossed over, but it's a full subsystem with lots of sort of embedded, independent systems that run themselves. They are nothing but a service that have a contract in gRPC. And so whether we run on real programmable logic and we control ions and we control RF signals, etc., or we say, hey, we have run this circuit, and this is the result. It doesn't matter, right? And that's kind of the power of sort of a software-only integration, figuring out the fidelity and the complexity and obviously the runtime of the simulator. That depends on what you are after. But from my perspective, as sort of the integrating all the components, that's our emulator, because the result is, if you will, in the integration or development, not important. Obviously, that becomes the most important aspect once you run a service, and we have the noisy simulator that runs on the platform. But that's kind of how we think about that. Was it helpful?
Okay, cool. Yeah, thanks a lot for the sharing, Yuri.
Good. Yeah. All right. And so finally, on the last slide, just kind of want to sort of remind ourselves that there's a lot of previous research done in different contexts of systems. So I come from the storage industry, and back in the early 2000s, storage was the most expensive part of computation, right? Before GPUs and before data centers. But so there's a lot of body of work that I kind of want to allude to that sort of look at a similar problem. How do we describe the capabilities of different storage systems? SSDs, large disks, slow disks, fast disks, disk drives. And how do we describe in a sort of something that's a highly nonlinear system, like a hard disk drive back, and how do we have software schedulers and something that has different competing SLAs, different cost structure? How do we kind of match those two together? So kind of I would recommend sort of reading the first thing mentioned here, Traveling to Rome, a retrospective on the journey. And so I'm not going to read the words on kind of what they were after, but basically the idea was, how do we declare what the capabilities of the system below, storage system is? How do we describe its attributes? And how do we then match it to basically optimize cost, speed, or all of the above sort of at the scheduling level by having those pieces? So there's a lot we can learn from. There's a lot that's different in our context, but from my perspective, someone who has worked pretty heavily in the storage industry. There's a set of attributes that are highly nonlinear systems that have some characteristics, and then we try to figure out how to optimize its operation from the data center perspective. And we have multiple QPUs and sort of scheduling decisions at different levels of the software stack. So with that, I kind of give the floor back to questions or discussion as needed.
Awesome. Thank you, everyone. Okay, we have a hand up already. Go ahead, Yogesh.
Thanks, Amit. Thanks a lot, Josh, Judy, and Spencer. Great talk. I had a couple of questions. Right, one was on you mentioned about reservation capability. I think one of you mentioned it on the chat as well, where you can sort of have back-to-back calibration with the job that's using the calibration. Right? Can you throw a bit more light on that?
Yeah, maybe I can.
Yeah, go ahead, Spencer. Yes, please.
Yeah, so on the platform level, yeah, if you're running something that has to be back to back, if you're doing noise profiling or something like that, we have users and organizations reach out to our people who are like user facing or corporation facing. They handle reservations with our system operators. So we make sure that like if you think your job will run within a 3-hour window, you own the QPU for 3 hours. And like we make sure we do not run calibration. Yeah, so we definitely like we have that option where if it's like a run that requires that, we definitely support it.
But is it possible for you to essentially say, hey, these are a pair of coupled jobs right next to each other, make sure that nothing else comes in between the two before you run those, something of that sort?
Oh yeah. So at least from the platform level, I know one, and then maybe Erie, I think you had something to add. At the platform, at the platform level, we have a hybrid service through quantum functions that have high priority. They submit to a high priority queue, and those are often not interrupted by a calibration. Yeah, sorry, Erie, go ahead.
No, this is great, right? So, in this picture, we have one queue, but as Spencer alluded to this, in reality, multiple queues, different priority, right? It doesn't, that's the queuing discipline. So what you described, Yogesh, is basically achieved by back-to-back of one tenant, one user, kind of a full reservational system. And so that's kind of what the automation schedule gets things. So as in the example of a 3-hour window, when we don't run a long calibration or something of that sort, obviously that's the reservation, and that's the exclusive access to sort of application that needs 3 hours and has lots of smart circuits that can be run in that 3 hours. But then is always what we call is something called interleave calibration, right? Where this is what the user or the platform isn't aware, and we always kind of do sort of a micro calibration. We're making sure that and so this is something that we kind of sneak in between, if you will, jobs. And there's many techniques. I can go into detail, but the idea is that there are things that we calibrate and micro adjust and figure out what it is, and there are things that sort of ensure that for the next 3 hours, basically 2.9 hours of the QPU time is just reserved for that, because there's always sort of some small circuit that we interleave every so often to make sure that things are fine, because we need to run exact circuit that we need with the parameters that we believe are appropriate to compile it and generate instructions and run it.
Great. Another question. So how do you sort of couple this scheduler with, let's say, a classical scheduler with the HPC? Because I see the classical part over here is on the quantum platform side in terms of post-processing and so on. But if you had something like a HPC queue that sort of fits in somewhere on the quantum platform sort of fork, right? Have you given some thought into how these two schedulers will orchestrate amongst each other?
Spencer, do you want to take that, or do you want me to?
I'll let you take that.
Right. So from that perspective, in this picture, right, the HPC scheduler really isn't there, right? So that would be kind of the level to the left, or the user is kind of that part. And indeed, that's kind of the next, so if you think of sort of abstraction, or, is a great, technique in computer science, right? So think of the HPC schedule as being to the left of our 3 layers here, right? And so indeed, but fundamentally, I intentionally use the word tenant, because whether the tenant is an HPC scheduler that has things to do, whether it needs, exclusive access for some time, we have ways to express this, and it's just a way of sort of casting it, as Spencer has shown earlier, in the language that the HPC scheduler that co-schedules CPUs and GPUs with our QPUs kind of interfaces along the interface with sort of the user level scheduler. And we have mechanisms already in place that allow you to do it, whether it's a reservation, whether it's a high priority, or the HPC scheduler user, quote unquote, right, will get priority access, but of course you can hog the system for indefinitely. So that's where the proportional sharing kind of comes in. So kind of we have done a lot of work in this. We continue refining this, but those are kind of initial thoughts of sort of balancing the fact. But from I sit in the middle in the gray box here. So for me, job is a job, user is a user as a job, and whether the job comes from a Slurm or HPC schedule or something else, that sort of is relevant because we have mechanisms to express this. We just need to cast it with the right level and priority and sort of a share of QPU time overall, right?
Okay. And last quick question, I know there are many raised hands in the pipeline that you had in the slide 16. Which is the most dominant stage?
Good question. It depends. If you have a three gigabit gates and 1 shot, it doesn't take that long to run it. But so obviously it depends on the size of the job, right? So I think the generation instructions takes a little bit of time. Loading is basically transfer speed, right? And there's because kind of we focused on flexibility and sort of a decoupling, right? There is an overhead in fetching the job. So it depends on the job, depends on what it is, but kind of the pipelining kind of sort of smears over the low throughput incurred through sort of lots of hubs and latency, right? So there's no sort of a silver lining, right? So we optimize for throughput, we maximize utilization of our GPU, and so pipelining is the effort. So it depends, right? If you have 5,000 shots and 10,000 native gates, or virtual native gates circuit, the execution will dominate. If you have a small circuit, obviously, lowering and generation of microcode and loading does take some time, right?
Sure. Yeah. Thank you.
Thanks. I have a quick question. You talked about the QDMI integration, and I know that you guys are also working on the QRMI integration. Can you just share a couple of quickly what the challenges on both and how they compare to each other?
Yeah, I'd be happy to. QDMI and QRMI, I really liked. They walk you through how a plugin should look, how an integration should look. Especially QDMI did a great job with that. It was very easy to generate a template to work off of. So I knew that when I was building the QDMI integration, if I filled in like X, Y, and Z, it was going to work just fine. That was that was the best thing I think about both of those integrations that I don't think you see as much with the first generation of Quantum SDKs that came out a few years ago. I think a difficulty that I have is that neither of them are very well tested in the environment yet. Hopefully that'll change soon. So for example, I mentioned the difference between this is QDMI is almost designed expecting a synchronous execution, but that's not the case when you're talking to an API. So even that level, that's another difficulty that I think we'll get through it, but that's not that's something to be aware of. Yeah.
Is that the same with QRMI, the asynchronous behavior? Both of them
Yeah,
have
that's
the same
right.
issue?
And
Okay.
I think it's true for anybody until they start integrating QPU level classical classical computation for dynamic circuits and classical control flows. That's kind of the distinction I'm making in my mind is QDMI and QRMI can be placed, it seems like, at either level of the stack. Right now we placed it at the quantum platform level.
Sounds good. I think the next person is Ryan. And please note, guys, we do have 7 minutes left, and we have a couple of other questions.
Sounds good. I'll go quick. So firstly, Yuri, Josh, and Spencer, this is really, really great to see. I've been looking forward to kind of seeing this high-level view of this. I'm going to drop my question in the chat too, just for posterity, or for provenance rather. Basically, what my first concern is, and I'm just curious. So Q estimation and QPU estimation time is something that we've been like talking about from the get-go when we were talking about first asking for co-schedulers long, long ago. I'm kind of curious, how good is it? Like, because when we were talking before we even had co-schedulers like QDMI and QRMI available, we were kind of trying to line up the double Q problem, but with using estimators alone. And the answer pretty much, and to be honest with this, with all vendors, was not very good, right? There's just so many things at play, and it's hard, depending on your workflow shape, it really varies. So I'm just kind of curious, like how good do you feel about it? How, like, from a ballpark perspective, how useful has it been in those estimations?
So it's all in progress, and the point is that you have a feedback loop, right? So I think how you define the model and how we refine the estimators in two ways, right? One is feeding the actual data that you take on the system, and the other one is kind of is the model, is the sort of the decomposition of the circuit into native gates and operations that need to happen, sort of, that are not really user circuits, sort of the unselect qubits and cooling qubits and all that stuff. That kind of is refined, and as we are learning the architecture, that's also that. So that's for the power of basically replacing the estimation model, both not just with real-time data. That's the easy part. That's just software engineering and collecting all the data along the right end. But it's the refinement of the model that you need to have, right? So our updates of the quantum platform software may include this, as well as we learn more, although there's a lot of effort made early on to sort of do this. So I think Ryan, you put a good point that it's a two-way street. You gotta sort of push and pull and tug from all sides, because there's no kind of a can answer. And we are refining, improving this, and as we roll new generations of systems, we will sort of figure out how good our estimator is. And I can tell you, probably won't be that good when we first roll out, but we will get better at it, right?
Excellent. Okay, I have more questions, but I'll go to the back of the queue and let someone else take a chance.
And Ryan, the one thing I will add, that is a very active field of work right now. So we'll have more to say probably in a quarter, but like give us about a quarter, and I think we might have more to talk about on estimations, but we're actively working on it. And
it's something that I'm going to be paying it. Yeah, but that's something. Real quick. That's something I'm going to be paying attention to when I do my workflow. And so I'll give you the feedback from what I come up with.
Awesome. Thank you so much.
Hiroshi, go ahead.
Okay, I have a very quick question. So before that, thank you for your great talk. Yes, and then please go for architecture diagram, maybe 14. And then when we think about the integration with the QDMI, there are several options. So you mentioned that you are thinking about the QDMI would be the left-hand side user and use IonQ quantum platform. But the other option maybe exists between the IonQ quantum platform and the quantum OS. This is another layer, and also there are another layer, the quantum OS and QPU hardware. So do you have any plans to or have some another interface between these two other boundary of the system for the QDMI integration or QRMI integration?
Josh, do you want to speak to that HPC roadmap?
And sorry, the question was specifically if we're planning to do more integration points than like the platform, Hiroshi, just to make sure I heard you right. Yeah, I think right now the short answer is no. We are considering it, but I don't think we're prepared to like really talk much about it. So like it has been something under consideration. Specifically what I can talk about is I think for latency purposes is like, we would like to see if we could get some lower hooks in there. But I will say one of our challenges is that like, our whole architecture makes a very big assumption up front that all jobs are coming from a cloud platform, or coming from something, I should say, that's like a cloud platform. So we are trying to evaluate what that looks like is the short answer.
Again, I can also speak to this if helpful, Josh. Yeah, I think one thing we're exploring right now is also NVQ Link. So NVQ Link is basically built to be a very close, tight connection at the hardware levels, at the lower levels of the stack that Yuri just talked about. That might be also an area where in the near future you'll see some integrations that we'll be building, but very preliminary as well.
So I want to interject here. Sorry, Yi had a question on the slide. He said, my question for slide 14, what's your perspective on tight coupling with respect to your current architecture designed for loose coupling in terms of workloads and use case scenarios? Yi, if you want to jump in.
Yeah, I think Gwen has pretty much answered my question there. Yeah, it is highly relevant to this MVQ link integration. Yeah.
Oh, sounds good.
Yeah,
Thank
one
And
thing
I would, yeah, go ahead, Gwen.
Yeah, one thing I wanted to just add to that, MVQ link is really built for superconducting qubits, or at least based on what we could see. Trapped ions are going to have a little bit of a different looking integration, mainly because our gate times and our coherent times are longer. So we don't actually need that very high bandwidth connection. So MVQ link might actually be a much more something that looks a little bit more like a loose integration, but tight enough to work for trapped ions.
Cool, thanks.
Yeah, and we are exploring kind of, so Spencer started with sort of the message passing asynchronous kind of the architecture with the message pass. Obviously we are learning that sort of the gRPC style, request response has some place in somewhere. And so we are sort of also figuring out what works best for that. And obviously, as you move the components from the platform into the Quantum OS, kind of figuratively speaking, right, or closer to the hardware, that benefits. I think, and if I am kind of there was a question about sort of how do we evolve, rapidly, and how do we evolve schema, and how do we ensure backward compatibility? Indeed, we are sort of heavily relying kind of on the really good practice of using protocol buffers. I mean, most of Google infrastructure is based on protocol buffers and gRPC like framework. So there's tested and sort of best practices in software development where that's not a problem, it's versioning, etc. I think the REST API and Open API kind of allows you to do this. I think gRPC and protocol buffers in particular has a sort of a even sort of a richer and more rigorous mechanism for ensuring compatibility. So we are practicing that, but at the end of the day, software engineering is art, a little bit of science, but mostly engineering and heavy work, right? So we could have a discipline, but I think using the right tools that I mentioned, whether it's gRPC, protocol buffers, ideal generation and automation and integration, all the way down, all the way up to Kubernetes, those kind of help us a lot to basically move along, right? And as you noticed, hint, hint, we have version 0.4, so there were previous versions, and we need to maintain compatibility for a reason. So we have figured out, but there's no magic bullet. It's just, good old-fashioned software engineering practice and following things and making sure that we don't break things by automation.
Thank you.
Did you want to ask something, Ryan? One last question? Or...
That was it. No, he answered my question.
Okay, all right, cool.
Yeah.
Awesome. This was a great discussion. Thank you, everyone. I think we're at the top of the hour now, so